Hello. So this is going to be our second video lecture about support vector machines. Okay. So so the last thing we talked about was that in support vector machines, um, this is the type of optimization that is being solved. C is a non-negative tuning parameter. Uh, C bounds the severity of the violence. C equals 0, no violation. So, and we get the maximal margin hyperplane if the data is separate. So, in other words, small c means a tendency to fit the data well, and that can lead to overfitting, large variance, small bias. As we increase c, then we are allowing more observations on the wrong side of the hyperplane. Okay, so C is an upper bound on the number of observations that are on the wrong side of the hyperplane. Okay, so here what we can see is that the largest value of C was used in this top left panel, and smaller values were used in the top right panel. When C is large, there is a high tolerance for observations being on the wrong side of the margin, and so the margin will be large. You see, all these red points are on the wrong side of the margin. All these blue points here are on the wrong side of the margin. These blue points are not only on the wrong side of the margin, but also on the wrong side of the hyperplane. As C decreases, the tolerance for observations being on the wrong side of the margin decreases and the margin narrows. So this is small c, large c. Now, how can we use this to create nonlinear class boundaries? We can use the same reasoning that we used when we were interested in having nonlinear models, nonlinear regression. What do? You add nonlinearities in the features, right? So here, for example, we have the features xij, and then we have xij squared. So why does this lead to a nonlinear decision boundary? What we have done is we have enlarged the feature space. So in addition to the features we have, we added these features which are the square of the original feature. So we are enlarging the feature space. So in effectively, the decision boundary in the enlarged feature space is linear, right? But since we are looking at it um, from the perspective of the original features, which are the xij's, it will look nonlinear, okay? So nonlinear class boundaries are essentially linear in the enlarged feature space, and we can make this even more nonlinear by adding higher order polynomial terms, interaction terms. Now the problem is that when the number of features increases, the computations become unmanageable. So the big problem that we have here um, by enlarging the feature space. So we are enlarging the feature space by adding nonlinearities, or we can also add interactions, is to capture nonlinear decision boundaries. The major problem is that when the number of features increases, then the computation becomes unmanageable. Now, support vector machine, uh, which I present next, allows us to enlarge the feature space um, without really having to do the computations in the enlarged feature space. Okay, so this is a support vector classifier. A support vector machine is an extension of the support vector classifier that results from enlarging the feature space in a specific way. And that specific way is done using something known as the kernel trick. The kernel trick allows us to enlarge our feature space in order to accommodate a nonlinear boundary between the classes without having to do the computations in that enlarged feature space. And how is that done? Um, so this is the original problem we want to solve, right? This is optimization problem we want to solve. Now, it is possible to get rid of m, and instead of maximizing beta, we can minimize the, instead of maximizing m, um, let me say this optimization problem is over beta 0, beta epsilon 1 to epsilon n, right? These two optimization problems are the same. In other words, you can reduce one to the other one and vice versa. In other words, if you solve this, you get an answer. If you solve this, you get the same answer. It's just two different ways of framing the same problem. Here, what we are doing is that we essentially are saying that, well, let's just remove this restriction, right? And if we remove this restriction, then the distance from the hyperplane will involve a division by the L2 norm of beta, right? And then if you do a little bit of math, you can show that that problem is essentially this. You want to minimize the norm subject to these constraints. So a support vector machine is enlarges the feature space for a support vector classifier. How to enlarge the feature space without adding computations? That's the main trick here. And the way it's done is using generalizations of inner products. Okay, so we have not discussed exactly how the support vector classifier is computed, um, mainly because the details are technical. It involves optimization, specifically convex optimization, specifically constrained convex optimization. And stepping into that topic requires a few lectures, and we do not have neither the time nor it is part of our syllabus, so we have to brush over it. But one thing I can tell you is that the solution of the support vector classifier involves only inner products of the observations as opposed to the observations themselves. So what I mean is that the xi's only matter as much as long, I mean, the only way that they play a role is through this inner product. So this is a bracket, and um, this is another way for writing inner product between two vectors. So this is essentially xi transpose xi prime. The reason that we use bracket is because we want to generalize this notion of inner product. So the linear support vector classifier in the end boils down to such a function, and it can be represented in this form where alpha i's are parameters estimated, so we need to estimate this and the beta 0, and there are n choose 2 inner products, and alpha I is only non-zero for the support vectors. Okay, so the support vector classifier only depends on the support vectors essentially. Okay, now suppose that every time the inner product appears, right, this inner product appears in the representation, we replace it with the generalization of the inner product. So we say K is a kernel that computes the inner product between xi and xi prime, right? It would be just x transpose x prime. But if we want to generalize this, we can use a polynomial kernel of degree d, which is this, or a radial kernel. So the polynomial kernel of degree d is the inner product plus 1 to the power of d. That's it. And if you expand this, we can write exactly what this inner product implies. In other words, this inner product is exactly x transpose x prime in an enlarged feature space where x is replaced by a function of x, which involves enlarging the features of x by adding nonlinearities and interactions. So this essentially amounts to fitting a support vector classifier in a higher dimensional space involving polynomials of degree d rather than in the original feature space. So when the support vector classifier is combined with a nonlinear kernel, such as this is a linear kernel because this kernel K amounts to the inner product, which we are familiar with. But when the support vector is combined with a nonlinear kernel, such as this, the resulting classifier, we call it the support vector machine. So this is one example of a possible nonlinear kernel, but we have other alternatives. And another popular choice is the radial kernel, which is essentially e to the power of negative gamma, the norm of the difference between x and x prime, where gamma becomes itself a free parameter. Gamma is a positive constant, and let's see. Okay, let's look at this. So what are we looking at? Here we have a data set, right, that is not linearly separable, at least in this original feature space. It is not linearly separable in the original feature space. Why? Because we have this cloud here, and then we have these two clouds. There is not a single hyperplane that can separate them. But if we enlarge the feature space, for example, using a polynomial kernel of degree 3, then we get a support vector classifier and these boundaries in the enlarged feature space. So it is linear in the enlarged feature space, but then when we bring it back to the original space, it becomes nonlinear. So these two boundaries. On the other hand, if you use a radial kernel, then this is the result you get. So you get this decision boundary, which again is linear in the enlarged feature space, but we are not plotting this in the enlarged feature space. We are plotting it in the original space, x1 and x2. So it becomes nonlinear and it's able to capture this cloud here and separate it from these two. So both kernels are capable of capturing the decision boundary. So what's the advantage of using a kernel rather than simply enlarging the feature space using functions of the original features? Well, the major advantage is computational, because the enlarged feature space might be actually a very high dimensional. In fact, it can be infinite dimensional. So the implied, here, let's look at this. All we need for the kernels is to find and choose two inner products. But the radial kernel, the implicit feature space, is infinite dimensional. So we wouldn't even be able to write it down and do the math here. So the nice thing, the major idea here is that we are enlarging it without explicitly enlarging the feature space. So we are benefiting from everything that comes with enlarging the feature space, that comes with adding nonlinear features without having to pay the cost of that, the extra computational cost caused by having by working in an enlarged feature space. So here's an example: heart disease as a function of age, gender, cholesterol, and 10 other predictors. And we want to compare support vector machines with LDA. We randomly split the data into 207 training and 90 data test. If you have such a data set, obviously it's not linearly separable. Then as if you use a nonlinear kernel, it becomes separable. And here are some results that plot the ROC curve for the heart data. So if you use a support vector classifier, a support vector classifier is a support vector machine that uses a linear kernel. So it boils down to a hyperplane. And when we are working with hyperplanes, then any like LDA, logistic regression, and support vector classifier, they're all hyperplanes trying to separate the data using slightly different cost functions, but they all perform more or less the same. But when we are talking about nonlinear support vector classifier, which is essentially a support vector machine, then you can see that the performances will be different and depending on what gamma is. So here gamma equal 10 to the power of -1 performs better than all other gammas we have here and the support vector classifier. Okay, so here's another example. This is the test ROC curve for the same data. First thing I want to draw your attention to is this. This is the train ROC. This is the test ROC. Obviously, the test ROC is a little bit lower, which means that the area under the curve for the train is higher, obviously. But what we see is that the support vector classifier and LDA more or less are the same, and for the test, actually they're are performing not very different from each other. which is just an example. It's not a rule. It can be different. But again, what we see here is that, a support vector classifier with gamma equal 10 to the power of -1 produces a low training error, but doesn't necessarily perform better in terms of test error. Okay, so what do we do when we have more than two classes? I already talked about this in one of the videos. That one way to deal with it is the one versus one classifier. So we have k choose two classifiers if there are total k. Another one is one versus all classifier. I talked in the previous video lectures about this one versus all classifier. So if we have k classes, we fit k SVMs each time comparing one of the k classes to the remaining k minus 1 classes. And that gives us k support vector machines. So if we have a test observation, we assign the observation to the class for which the distance from the hyperplane is largest. This amounts to the high level of confidence that the test observation belongs to the kth class rather than any other class. So one versus one classifier, we have k choose two classifiers, assign test to the class most frequently assigned, right? Because when a test observation comes, we apply these k choose two classifiers to it, and then we assign it to the class most frequently assigned. When we talk about the one versus all classifier, we have k classifiers, one versus the k minus 1, and then we assign x star to the class for which fk x star is largest, high level of confidence. Fk of x star is proportional to the distance from the hyperplane for the kth classifier. So essentially having a hyperplane that allows some violation, that's not new. What is new for support vector machine is expanding the feature space without the added computational cost. That's the new thing. And let's look at this again. This is what the support vector classifier is about, right? So this is the problem we're trying to solve. And with a little bit math, we can show that this optimization problem is the same as this. Essentially, we just take this epsilon I to the other side and take this to this side. And this is our fx. This is our f, right? This function is what we call our f. And if we do a little bit more math, so this is a constraint optimization problem. A constraint optimization problem can be turned into an unconstrained optimization problem using the Lagrange multipliers. Again, this is beyond the scope of this lecture, but if you're interested, you should look for Lagrange multipliers. So, I mean, the Wikipedia is not the best source necessarily, but just because it's standardized, I wanted you to see Maybe my pronunciation is not perfect, so this is what I mean by Lagrange multiplier. Anyhow, these two optimization problems are the same, and these two are the same as this one. So a support vector machine is essentially solving this unconstrained optimization problem. We have removed C, but we have now, instead of it lambda, we have the L2 norm of beta, and then we have the max between 0 and 1 minus yi fxi. If lambda is large, more violations are tolerated, low variance, high bias, right? If lambda is small, then less violations are tolerated. Again, this is a measure of fitness. This is a measure of fitness, and this is a measure of complexity, and lambda is a tuning parameter. Okay. Now, as I said, this is a support vector machine. Logistic ridge, logistic regression with the ridge penalty. We talked about this before. It can be written in this form. This will be the logistic loss, and this is what we know as a hinge loss. The penalties are the same, so you see that the support vector machine and logistic regression are similar. This is a measure of how well the data, the model fits the data for support vector machine, and this is how well the model fits the data. So it's overall observation. So this is a cost function per observation. Now you may say, wait a second, why is this different from the form of the log likelihood for logistic regression, which we talked about before, right? And that's a valid point. The main reason here is that this logistic regression here is formulated using yi being equal to 1 and yi being equal to -1, as opposed to yi being 1 and 0. Okay. So let's look at this. This is an alternative way of looking at logistic regression. If we use 1 and -1 as our labels, as opposed to 1 and 0, before we did 1 and 0, now it's 1 and -1. It's the meaning is the same, it just changes the formulation a little bit, and I want to show you where this comes from. Now, remember that beta transpose x plus beta 0 is our f, right? And if y is equal to 1, this is our probability. Now, if y is equal to -1, it's 1 over this, so we don't have this term, right? So before we had 1 and 0, and now it's 1 and -1. Now you can write this in this form. One second, sorry, there's a mistake here. Let me correct that. No, actually, there is no mistake. So if y is 1, you have 1 here, so you have 1 over 1 plus e to the power of negative beta transpose x plus beta 0, right? So this is correct. This is also correct. But that's for -1. So how can we combine these two? Here. This is how we combine them. So probability of y given x is equal to 1 over 1 plus e to the power of negative y times beta transpose x plus beta 0. If y is equal to 1, then you have 1 over 1 plus e to the power of negative beta transpose x plus beta 0, which is equal to this. On the other hand, if y is negative 1, then you have 1 divided by 1 plus negative times negative gives you 1 e to the power of beta transpose x plus beta 0, which is this. So we combined these two into this one formulation. Now if you take the negative log of this probability, yes, it is a probability, but in this context we call it a likelihood because we are interested in beta and beta 0. And if you take the log of this, you get log of 1 plus e to the power of negative. There is no, this transpose shouldn't be here. Y is 1 and negative 1, so the transpose here is irrelevant. So just ignore this. Let me just correct that here. So you have negative y beta transpose x plus beta 0. So this is a cost function per observation for one observation. This is our loss function, which is the same as we have here. So I just wanted to spend a minute explaining why this looks different from our previous negative log likelihoods of the logistic regression. There's nothing deep going on here. It's just because we use the 1 and negative 1 labels as opposed to 1 and 0. Okay, so now what's the difference? So you see here both of these are functions of yi fxi. So we are curious to see if we plot this quantity, the logistic loss versus the hinge loss as a function of yf. And here on the horizontal axis we have yf. On the vertical axis we have the loss, the logistic loss, and the support vector machine loss behave similarly when these two are big, when these are big, because it's just close to linear. But the logistic loss smoothly goes to 0. The support vector machine hits 0 and then it is remains 0. So this is what the robustness is about. You see, any error in this area does not incur any cost, and that leads to the robustness of support vector machine. Any violation within this region does not incur any loss. It's after this that we have a linear loss. Okay, so this summarizes what I wanted to say about support vector machines in terms of the theory and the meaning. But next I would like to show how to perform support vector machine classification in R. So I'm coming back to the college data that we discussed before in the context of trees and logistic regression, right? So um, we loaded data, it's binary, um, we fit lasso logistic, then we fit elastic net logistic, then we fit ridge logistic, and then we do support vector machines. And in order to do that, we need to create a data frame where we include our feature matrix and response matrix. Make sure we code it as a factor so R knows that this is a categorical variable, not a numerical. And then we say, okay, do cross validation for support vector machine y. The kernel is radial, and then there are two parameters that we need to do cross validation over. One is the cost, the other one is gamma. Gamma is so for a radial kernel, this is gamma here. And it's a free parameter that we need to do cross validation over. For example, if you have a polynomial of degree d, you don't have that gamma. Or if you do a linear kernel, you don't have that gamma. But here we have it if you use a radial. And we just provide some numbers. These numbers are arbitrary, but we can just do the cross validation over a set, right? And the cost argument, the cost argument here allows us to specify the cost of a violation to the margin. So when the cost argument is small, then the margin will be wide, and many support vectors will be on the margin or violate the margin. When the cost is large, so this is the cost, as the cost increases, the margin will become narrower, right? And there will be a few support vectors on the margin or violate the margin. And when you do a radial kernel, you have these two parameters which we need to do cross validation over. If we do a linear kernel, then we only cross validate over the cost. If we do a polynomial of whatever degree, then we only have the cost. So the gamma only shows up for a radial kernel. Then after it's tuned, this is saved into this function tune.svm, and then we would like we just choose the best model that will be an SVM, and then we give it to the predict function, and then the predict function just and the data, and then we get the prediction labels for the training data, and then false positive, true positive, etc., etc. Okay. Now, if you wanted to do a support vector polynomial degree, then you just say polynomial. You introduce the coefficient and the degree, what degree you want. Okay, so if you look at the support vector machine function SVM, you can just spend some time look at what the options here are. So as you can see, in addition to the linear kernel, we have the polynomial, we have the radial basis, and there's also another one, sigmoid. But the polynomial is slightly different from what we talked in the slides. It has actually also a free parameter of gamma and the coefficient and the degree. The coefficient is just a constant here. And for example, I just put 1, and then degree, and the default is 1 over the data dimension. So if you don't specify it, just 1 over the data dimension. And here you just do degree 10, and you can just substitute this here and run this polynomial, but then you have to also specify the degree. So it's pretty straightforward to fit a support vector machine to the data. And then let's see, that's it, yes. So trainer type 1 error for lasso is 0.14. What happened? Oh, it's super. And for a radial SVM is 0.08, 0.01. So this is how you can fit a support vector machine to the real data. And also do prediction, right? Here we're doing the predictions. Now let's look at this function a little bit. It says tenfold cross validation. The best parameters are cost1, 0.01. Now you may ask me this: how do you find cost1 and parameter? I mean, how do we know this is the right range? Well, when I see that this is the best parameter, when I see cost1 is the best parameter, what I would do is I would just remove this, and I would remove this 2, and I would just say, okay, let's do this 2, let's do 4, and here let's add 0.5, right? So I'm adding a little bit of resolution in the region around what I think is a good thing, right? 1. And then when the gamma, the best gamma is 0.1, that means that this 10 is probably just, we don't need this. We have this 1, so let's just add 0.25, right? And then we have 0.5, but then also go a little bit down, just remove the 1, and then we have 0.05, 0.025. So notice that, first of all, unlike the GLMNet, which when you run the cross validation, if you do not provide the range of lambdas, it automatically can find a reasonable range. But for support vector machines, you have to provide it, and the way to do it is using trial and error. So let's see. I am curious to see what cross validation will tell us about the best cost and best gamma. Now, because I have increased this, let's see. Okay, you see now the best parameter is 4, and gamma 0.025. So it's just going to the extremes. Notice that the cost has increased. When the cost increases, we can reduce the number of training errors. Okay, so let's try 8 and 0.00125. Just make it like this. 0.001. And then we have 16 here. Actually, because I increased the number of values for the tuning parameters, cost and gamma, the cross validation is taking longer. Okay, let's see what is okay, so gamma is the best gamma is this, the best cost function is that. So, you know, whenever the optimum hyperparameters are found at the boundary, which here is 16, we want to add more just to make sure that it's not there's that to make sure that there's no better answer around there. 0.01, so I guess we can get rid of this and maybe add a 0.05 here. Let's run this again. Okay, cool. So we kind of found the best parameters. Let's see what Tune SVM, what else does it offer? So for cost and gamma, we have the error and dispersion. For all these pairs of values we have considered here. For all these pairs, these are the errors and these are the dispersion. And we see that the minimum happens here. For these two combinations of cost and gamma. Okay, so this is one example. There will be another example where I will compare random forest to support vector machine, and there will be an R code essentially. And I hope this was useful. Thank you.